Hey guys, Mr. Riz here to help you out with the start of the 3.1 lesson in calculus. So our goals here is to make sure we can understand the definition of the extrema of a function on an interval. And we also want to make sure we can understand the definition of relative extrema function on an open interval. And then our final goal is to make sure we can find extrema on a closed interval. So what are extremas of a function? So in calculus, much of the effort is devoted to determining how the behavior of a function f on an interval I. So in some space, how does that function work? Does f have a maximum value in that interval? Does it have a minimum value? Where is f going up, increasing? Where is it decreasing? So in this chapter, chapter 3, we're going to go through all those different things, and we're going to learn how the derivatives can be used to apply or get these answers to those questions. So the first thing we're going to do is look at extrema. And there's two types of extrema that we can have. We can have mins or maxes. And this is the real big lengthy definition is, but a minimum is the f of whatever value where it's lower than any other f value during that time. So if we look at this graph here, like this 0.01 is the minimum because only at 0 we get 1. Nowhere else on this function do we get a lower value than 1. And then over here, 2,5 is the maximum because at 2, we get a y value of 5, and nowhere else on the graph do we get a y value higher than 5. Now, this works for this continuous function because it's on a closed interval from -1 to 2. Now, if we have an open interval, meaning we don't include those endpoints, we still have a minimum here because that's the lowest point, but since those are not actual dots on the graph, we can't assume that those are maximum. So that's a little nitpicky there, but for the most part, we're going to look at just closed intervals because they're the easiest ones to do math with. Okay, and then same thing too, if this was an open dot here, that would not be a minimum. Okay, so the biggest thing that we need to know first is that if f is a continuous function from a to b, then f has both a minimum and a maximum value. So as long as we have a graph and then we have a continuous function, so that function doesn't jump up at all or it doesn't have a hole in it, but we have a regular normal continuous function, there's going to be a minimum and a maximum in that section. Now, they might be the exact same thing. If it's a straight line, it's the exact same thing, but there is a min and a max. Okay, next we can talk about relative mins and maxes. So relative mins and relative maxes are the minimums or maximums of specific points. So if we look at this graph here, we can say that this area here is a relative max because just relative to this section here that's shaded pink, that's the highest section of that region, but it's not the absolute max. You can see here the graph does get higher and higher and higher. So there are points that are higher than this spot here, but it's not the highest. And then same thing down here, we have a relative min because this is the lowest point on the graph relative just to only that section there. So any hills or valleys are going to be your relative mins or relative maxes. They become absolute maxes or absolute mins if they are the absolute lowest or the absolute highest across the entire function. All right, and so just more examples here. Yes, these functions continue on, but we got some relative maxes and relative mins, and then even with sine functions, they alternate back and forth. Okay, now the one thing that we want to know is, okay, how do these relative mins and relative maxes associate with calculus and derivatives? And these special points are known as critical numbers. Any critical number here, we'll make a note, is when we have a horizontal tangent or when the derivative does not exist. And so the most part, and we actually have the definition here, is we can find these critical numbers when f prime of c equals 0. So we've done a lot of time taking derivatives. Here's what we're going to do now in this chapter is we're going to find critical numbers, and those critical numbers are when f prime of 0 equals, or f prime of c equals 0, or when f prime of c does not exist. Those are going to be spots that we're going to make sure that we note and we plot on our graphs. Okay, now if f prime of c equals 0, there's a really good chance that that point is a relative min or a relative max. It's not a guarantee that it is a relative min or relative max, but there's a really good chance. Okay, so the first thing that we're going to do is let's just look at open intervals. So let's look at some of the homework problems that you guys will do. You guys have worksheet A here. what you're going to do is determine the value of the derivative if it exists. So I'm going to go through some of the odd problems here and leave the even ones for you guys to do. So first thing what we're going to do here is we're going to find the value of the derivative at the points that are on the graph. So on this problem here, we got the equation here, we're going to plug in 0. Now there's two ways that we can do this. We could take the derivative of this expression here, which we'd have to do low d high, high d low over low low. Or if you guys remember, this is why we have our calculator, to make our life easier. We already know how to do low d high, high d low. We'll have to do it later on when we do more intensive things. But for right now, we're just trying to find the value of the slope there. And so this first problem, all right, we got x squared divided by parenthesis x squared plus 4. Go ahead, we can graph that in there. That's what we got. And remember, if we do second calc and we go down to 6 dy dx and type in our x value, which would be 0 at that point, it will tell us the slope at that point, and dy dx is 0. Okay, that has a slope of 0. We might notice a pattern here. Let's skip 2. You guys will do 2 on your own. Tell me the slope of those 2 points there. All right, let's check out 3. Take the equation. Now we could do the derivative and make this a 1 plus, okay, whatever that is, and plug in 2. But okay, let's just make the equation, type in x plus 4 divided by x squared. It should work out. Graph that. Okay, that's what we see. Now we're only looking in this spot here at number 2. So we're going to do second calc. Pick 6 for the derivative and type in our x value of 2. All right, we get negative 5 e to the negative. So that's negative 0.000005. That's a 0. Okay, so the derivative is 0. All right, what about this one here? All right, what do we get? All right, x plus 2 to the, should be to the 2/3 power. Graph that, okay. And we're going to try to find the derivative at negative 2. Second calc, 6, negative 2. All right, we get 0. Noticing a pattern here, we got 0, we got 0, we got 0. And if we look at all these points, we know that those are relative mins or relative maxes. Those are highs and lows on the graph. Derivative equals 0. All right, next, if we're just looking at this graph here, not knowing the function here, can we determine whether we would have any critical numbers? And that's where the derivative would equal 0. So remember, the derivative would equal 0 anytime we would have a horizontal tangent. So if we think about it right here, we'd have a horizontal tangent, and that lines up with 2. So we can say that there is a critical number at x equals 2. Now, looking at that point there, we could say that point is at 2, 4, and we would describe that point as an absolute max. Okay, so go through and describe those. All right, yes, same thing here. Let's look at this problem. Okay, where would we have horizontal tangents? Okay, we have one here, one here. We actually would have one kind of here, like in that one problem that we just did, that one. So, okay, we have critical numbers at x equals 1, at x equals 2, at x equals 3. Now, we don't have them at 0 and 4 because those are open dots and those are not actual points. And we could say, well, at 1, 3, and also at 3, 3, those are absolute maxes because those are the highest points on the graph. It doesn't get any higher. And then we can actually say at 2, 0 is an absolute min because that's the lowest point on the graph. And even though we have open dots there, so that's the only point on the entire graph that it equals 0. All right. And now for the last problems, 11 and 13, those types over there, let's go ahead and plug these into our calculator to see what this looks like. Okay, so find the critical number. So we just want to name where we would have critical points. All right, we look here. Let's type this in. We got x cubed minus 3x squared. Now, if we wanted to, we could just, this is what, let's do this without the calculator first. If we're going to do this the math way, what we want to do is take the derivative. And the derivative of this is 3x squared minus 6x. Remember, critical numbers is where the derivative does not exist or where the derivative equals 0. And so we could factor out the 3x here, and we would get x minus 2. So if we set both of these equal to 0, 3x equal to 0, that means we should have a critical number at 0. And then Plug this one in, x minus 2, we get another one at 2. So let's use the graphing calculator to help look at this up to verify those answers. So I think we're going to have one at 0 and 2. Oh, I already had it typed up. We'll type it up again, minus 3x squared. All right, there's one at 0, it's flat, and then over here at 2, it'd be flat again. So we were right. And so if we look at number 13, yeah, that might be a little crazy. We'd have to do the chain rule with the product rule. So calculator time, let's see how this would be easy. X, and then we got the square root of 4 minus x. And if you look here, we have a high point here. Now, if you've never done this before, we can actually find the maximum and minimums on our calculator, like how we did with, finding the zeros. We can do second calc, and we can ask it right here for step 4 to find the maximum. Tell me the highest point. So the highest point looks like it's somewhere in between 2 and maybe 2 and 3. Yeah. So we can say x is 2, right is 3. We can guess where it is, but it will tell us that that's at 2.66666 or 2 2/3. So the critical number for this one here, let's see, that'd be at, well, t in this case, 2 2/3, which would be, what is 2 2/3? 3 times 2 is 6 plus 2, that's 8/3. And I'm sure if we did the derivative and set that equal to 0, we would get 8/3. All right, guys, so there's part 1 of the 3.1 section. What we're going to do next is kind of get a little bit more in depth with it and make sure we understand this. You guys have a great day, and I will see you guys next time.